Okay, this is the lecture for the in-class lecture for November 12th. So when we last week we talked about the naming and EZ naming, cis-trans, and IUPAC naming for alkenes. And once you get past their physical properties and all the basic information, the next thing we do for a functional group is we talk about how to make that. And so this is going to be a review because we've already talked about E1 and E2 reactions and how to convert an alkyl halide to its corresponding alkenes. Now for 2-chlorobutane, we've got the alpha carbon and the 2 beta carbons, each of which have a beta hydrogen. So we could form 2 different alkenes from this molecule. We can form that one, and we can form this one. And so one of the things that we have to think about is if I'm going to convert, or if I'm going to synthesize an alkene, E1 is probably not going to be a good mechanism because the alkyl halide, in order to make it undergo E1, you're going to get a little SN1 product to go with it. And so you would just heat it. And so the best methods to make alkenes from alkyl halides is to use E2. And so your choice here is to use either NH2- or tertiary butoxide minus. So the question is which reagent goes on which arrow to form the products. And for this, if I want to form this molecule, the top molecule, then I'm going to have to remove a hydrogen that is the most accessible sterically. So therefore, I'm going to use the tertiary butoxide ion. And that's going to give me, in general, the least substituted alkene. Whereas if I want to form the double bond in the middle of the molecule, I need to remove a less or a more sterically hindered hydrogen. But the key is that when I react NH2- with an alkyl halide, the NH2- can get at either one of the 2 beta hydrogens and therefore will form the more stable, more substituted product. So when we make alkenes from alkyl halides, we're going to do it by E2, and we're going to have to make the proper choice of tertiary butoxide and NH2 ions to give me either the most substituted or the less substituted product. Okay, so that's one way to make alkenes. Another way to make alkenes is to start with alcohols. So let's say I start with 2-butanol. And in this case, it's going to take a different set of reagents to have this alcohol undergo elimination. First, I have to realize that OH- is a pretty strong base and a very poor leaving group for SN1, SN2, E1, or E2. And so therefore what I need to do is I need to convert this OH- into a better leaving group. Now, how did I know that OH was a lousy leaving group? Because remember, basicity is inversely related to leaving group. Strong bases make very poor leaving groups. So what I'm going to do this reaction is I'm going to simply add acid to this. And so the OH is going to become protonated to form an oxonium ion. And we're going to learn many reactions throughout the course of the year where when we add an acid to an alcohol or to an oxygen-containing molecule, the first step is always going to be protonate the oxygen, and this is no different. So once I protonate this OH group, it becomes water. Well, we know that water is less basic, and therefore water is a better leaving group. And so what I do by protonating the OH is I convert it into a better leaving group. So this water molecule then can leave. Now I'm looking at a secondary alcohol. We classify alcohols based on the carbon that the OH group is attached to. So it's a secondary alcohol because it's attached to a secondary carbon. Since I have a secondary carbon, I can very easily break the carbon-oxygen bond, and that's going to give me a carbocation. and then water as my leaving group and product. Now at this point you should be thinking there's nothing really new here because we've added the water to the carbocation to form the oxonium ion, and we've lost an H plus from an oxonium ion to form an alcohol. So all I've done here is written the 3 steps that we write for sort of the inverse steps of SN1 addition of water to a carbocation. So now if I look at the fact that I've got 2 beta hydrogens, right, because I've got the 2 beta carbons with beta hydrogen A and beta hydrogen B, I can now take the HA, and if I lose HA plus, I'm going to form the alkene, which I'll call product A. And if I lose HB plus, then I'm going to form that alkene, which I'll call product B. Now what mechanism is this? This right here is E1. That's what we learned last week for an E1 mechanism, maybe last week or the week before. What's the major product of this E1 reaction, product A or product B? If you said product B, you're correct because E1 always produces the most stable, which means the most substituted alkene, which in this case is product B. So notice that I'm doing this reaction by combining a couple of things that we already know. We already basically know that these first 3 steps are the reverse of weak nucleophiles adding to carbocations. So I can't have the OH group leave on its own. I need to protonate it. I protonate it, it forms an oxonium ion. That water molecule makes a better leaving group. This is a secondary position, so it leaves to form a carbocation. And then I lose beta hydrogens to form the 2 possible products. And this is an E1 mechanism, so the most stable product is the one that is formed as the major product. Okay, so this is what happens. This mechanism is what would happen if you had a secondary or tertiary alcohol. And overall then, I would call this mechanism E1 because it goes through a carbocation intermediate. I'm going to broaden my definition of E1 and E2 to be E1 goes through a carbocation intermediate and E2 doesn't. E2 only goes through other intermediates such as an oxonium ion, but not a carbocation. So what would happen if I did an elimination on a primary alcohol? Well, I would add my acid to the primary alcohol. I would get protonation. And that's going to form this oxonium ion. Now, unfortunately, the water can't leave because I can't form a primary carbocation. So if I'm going to do elimination, this is my alpha carbon, this is my beta carbon. So I do have one set of beta hydrogens that could be lost. Before I do this mechanism, before I finish it, doing eliminations on primary alcohols is actually pretty easy because if the primary carbon is the alpha carbon, there's only one set of beta hydrogens, so there's only one product that can be formed, so we don't have to worry about multiple products. So I protonate the OH to form the oxonium ion, but now I need to do this concerted, so I need to have this CH bond break, have the pair of electrons move like that, and then have the pair of electrons move to this oxygen to then form my final product, and now the water molecule, and an H plus, which was lost as the beta hydrogen. So in this case, it's a one-step mechanism. And I would classify this, and I'm going to put this in quotes, as an E2 mechanism because it does not involve a carbocation intermediate. Now, technically, it's not really E2 because there's no two species that are reacting together. So I just call it E2 because that's sort of consistent in terms of the fact that we don't have a carbocation intermediate. So we do have this rate determining step being concerted. What would the transition state for this last step be? Well, I would have a partial carbon, beta hydrogen bond. I would have partial double bond being formed. That's my CH2 partial bond to the oxygen. So there's my partial bonding scheme for this transition state. Where would the delta plus charges go? There would be a delta plus charge on the oxygen as it goes from oxonium ion to neutral water. And there would be a delta plus charge over here on the beta hydrogen. So this would be the transition state for this elimination reaction. And this would be a concerted elimination, so therefore we would call it E2. Now, overall, if I look at these two reactions, what I'm doing is, if I just rewrite this reaction, I am losing H and OH. So I'm losing H2O to form the final alkene. So this reaction is actually called a dehydration reaction because I'm losing water in the process. Okay? So dehydration is what we do when we react an alcohol with acid, and I'm going to throw in another reagent called heat in a minute, but that's what we call these overall reactions, is these are called dehydrations. And I'd also like to step back here because I forgot to say this in the 8 o'clock class, that when you have a secondary or tertiary carbon that can give more than one product, we always form the most substituted product because this reaction actually would then go through an E1 mechanism, and E1 always gives the most stable product. This is actually the series of reactions that Zaitsev did in order to formulate his rule. Zaitsev did not react alkyl halides in eliminations. He actually dehydrated alcohols with acid, and what he found was that he always got the most substituted double bond when he did that reaction. So that's where actually Zaitsev's rule comes from, is dehydrations of alcohols. So we can do eliminations then with acid being required. We need acid to protonate the OH group to make it leave. If it's a primary system, then we won't go through a carbocation. If it's secondary or tertiary, we will. So the next question that we have to ask is, well, what is this H+? Where does the H+ come from? Could I use, as my H+ source, could I use HCl, HBr, or HI? Well, what would happen if I took, for instance, isopropyl alcohol and added H+ Cl- to it? If I start doing that mechanism, I would protonate my OH group to form my oxonium ion. And then, since this is a secondary system, I would break my carbon-oxygen bond. So I would get my carbocation and water. And the idea here is that if we want to do elimination, I want to eliminate nucleophiles that will react with the carbocation. Now you say, but you still have water here. Well, yeah, I'm always going to have water there. And if water was to react with the carbocation, then I would reverse my steps in order to form the final product, or actually not the final product, the starting material, the starting alcohol. So if I used HCl to do this reaction, the Cl minus would be present. It's a strong nucleophile. It would simply come in and react, and I would make isopropyl chloride. So if you think about this, what I've done is, if I want to substitute for an OH group, I just need to add HX, add HCl, HBr, or HI. First, I need to protonate this OH group. The OH group won't leave on its own. So if I took isopropyl alcohol and I just reacted it with chlorine or chloride, I would get no reaction because the OH group isn't a strong enough leaving group to leave on its own. I need the presence of the acid in order to do this reaction. But if I want to do elimination, I can't have any nucleophile present. So I'll talk about that in a moment, but I just want to sort of give you an idea here that that's okay, because now I can do SN1 or SN2 reactions, and now I've got a new leaving group to add to the mix. Before I just had alkyl halides, but now I have an OH group that can leave. The only issue is I've got to protonate it with acid first. So we could do substitution. We could do SN1 like I did here. We could do an SN2 reaction, like reacting a primary alcohol with H plus and Br minus. You might say, well, that sounds awfully familiar. And the reason it sounds awfully familiar is because last week, or whenever you in lab, you took sulfuric acid, which was a source of H plus, and you reacted that with 1-butanol along with sodium bromide, which was a source of Br minus, and you did an SN2 mechanism to form 1-bromobutane. And so in this case, we could have used H plus Br minus, but we instead used sulfuric and sodium bromide. But I did an SN2 reaction. Why was it SN2? Because there's no carbocation intermediate, because this is a primary alcohol. So I protonated my OH, my Br minus came in, and then kicked off the water molecule to give me my final product. So we can now expand our reactions to include alcohols in doing not only eliminations, but also in doing substitutions. And we can even have carbocation rearrangements occur. And so this is, if I take this molecule and I was to add HCl, I would actually do an SN1 mechanism, and I could get a rearranged product. So now we have carbocation rearrangements in the mix starting from an alcohol. And this reaction, writing the mechanism of this, is your take-home quiz for Wednesday, November 14th. And if you're having some sense of deja vu there, this is very similar to an exam problem. So if you missed that exam problem, you might want to go and take a look at the exam key as you look at your exam. But this will be the take-home quiz. There will not be an in-class quiz on Wednesday, nor will there be an online quiz. This will be the only quiz for Wednesday, and so you're going to write the complete mechanism for this. And as I record this, I just posted that to the 8 o'clock class, and that quiz will then go to the 9 o'clock class as soon as I'm done recording this lecture and putting it online. Okay, so what is my point? That's a good question. My point is this, that if we use HCl, HBr, or HI, I'm not going to do elimination, I'm going to do SN1 or SN2. That's useful because now I'm going to be able to convert an OH group to a halogen. But remember, I started this by saying, how do we make alkenes? So what is the H plus source to make an alkene? And it turns out that the H plus source is either going to be sulfuric or phosphoric acid. And so in this case, I'm going to take and I'm going to react my alcohol with, let's say, H2SO4 and heat. And sometimes you'll see a triangle or a capital delta as a symbol for heat. And that's going to form then my most substituted product, my most substituted alkene, as the major product of the reaction. In other words, the most substituted alkene. So I can use phosphoric or sulfuric acids to do these reactions. Now, if I'm going to do elimination, what I really need is I need to use an acid whose conjugate base is a lousy nucleophile. We know there's two factors that go into nucleophile strength. One is basicity, if it's vertical or diagonal relationship, and the other is the polarizability. So weak nucleophiles are going to be either weak bases or weakly polarizable. Now, polarizability isn't going to come into play here because that's normally what we do when we use when we're comparing single atoms or single anions. So HSO4 and H2PO4, these are both very weak bases. And so I would ask the question, well, why are they very weak bases? Can you give me an example, or example why they're very weak bases? And the first one you might come up with is, well, because these are strong acids, and the conjugate base of a strong acid is, well, usually a non-acid or non-base, which would be good because then these would be very poor nucleophiles. So that's one answer, is these are both very weak bases because H2SO4 and H3PO4 are strong. There's another reason though, and that is that if we look at this equilibrium, and this is the equilibrium that you would have for an acid dissociating into its conjugate base and then freeing up H+. The more this equilibrium is shifted to the right, the stronger the acid you have. Okay, the more it's shifted to the right. And so anything I can do to shift this equilibrium to the right is going to make this acid stronger, which then by definition is going to make this conjugate base weaker. Well, in general chemistry, we talk about shifting equilibria using Le Chatelier's principle, which involves increasing or decreasing concentrations. That's not what I'm going to do here. Instead, I'm going to say that the more stable you can make the conjugate base, the weaker it will be as a base and therefore as a nucleophile. Because if A- is very stable, it's not going to want to react with H+, and therefore it's not going to want to react too much as a base. So what makes HSO4 and H2PO4 very stable anions? Well, if we draw the Lewis dot structures of them, we're going to find something like this, or something like that. Why are these very stable? Well, if you said they're stable because they have lots of resonance structures, you'd be correct. So these form very stable anions because they have lots of resonance structures. The more stable they are, then, the more they're going to push the equilibrium to the right, and therefore it's stronger conjugate acid, the weaker the conjugate base. And sometimes people will say, well, these are also lousy nucleophiles, because remember, the whole point is that once the H plus protonates the OH, I want the conjugate base then of that acid to not act as a nucleophile, so I can do elimination and not substitution. Well, one of the reasons that people will oftentimes say is, well, these are lousy nucleophiles because of sterics. And I can't argue with that. They are pretty lousy nucleophiles. But really, it's the basicity that plays much more of a role. They're very weak bases because they are very stable anions. So that means that if I'm going to do this reaction, I need to use H2 SO4, heat, and acid to do this reaction. Okay. Now, if I do this reaction, I'm going to form the most stable product. And that's basically where Zaitsev came up with his rule. Now, I have one final thing about this reaction, and that's this. If I was to go back, to the beginning here, and we look at this mechanism, and I just focus on this, let's say this part of the mechanism to form product A. Or better yet, let's focus on this part of the mechanism to form product B, the major product. I would then ask the question, well, what is the role of H+? What's the role of the acid? Is it a reagent? Well, it's not a reagent because it is used in one step, but then it's regenerated in another step. So it's not like it's consumed and that's the end of it. It's consumed and then it's produced in a step later on. So what would I call something that is consumed in one step of the mechanism but produced later on in another step, so that the net result is that it's neither a reactant nor a product? And if you said that H plus is the catalyst for this reaction, you would be correct. So H plus is a catalyst. It speeds up the reaction. If you just take an alcohol and you heat it, I suppose you might get a little bit of elimination, but you'll get it a lot faster if you add H plus. Okay. Now, H plus in dehydration reactions then is a catalyst. Is it a catalyst in the substitution reaction? So is H plus a catalyst up here in this substitution reaction? Is it a catalyst in the reaction that you did for lab, or the lab reports due this week? Is H plus a reagent or a catalyst in substitution? In elimination, it's a catalyst, but actually in these substitution reactions, it is a reagent because it gets consumed in one step and then it's never regenerated. It actually goes with the water. And the same thing's true down here. What are the products over here? The products over here are water and HSO4 minus. So in substitution, the acid is a reagent, but in dehydration, since it's consumed and produced, it's now a catalyst. Okay, and so that's how the role of acid differs in dehydration versus in substitution. Okay. So what I've talked about today is the idea of making alkenes. But not only just making alkenes, but then using a similar reaction, only having a nucleophile present like HCl, HBr, and HI to make the OH group leave, but then have a nucleophile come in and attack the carbocation to do substitution. So this is going to open up a lot of reactions that we could do either to prepare alkenes or to substitute OH groups for to make alkyl halides. Okay, and so that's what we're going to talk about, and we're going to do problems on Wednesday. There won't be a lecture video for Wednesday. There will be one for Friday, but not for Wednesday. There won't be an in-class quiz. There won't be an online quiz. However, there is that take-home quiz for Wednesday where you're going to basically react HCl with that alcohol and do a substitution, an SN1 rearrangement reaction to give you the alkyl halide product. Okay, and so that will be the only thing that will be due for Wednesday. On Wednesday, we'll do more of these SN1, SN2, E1, and E2 mechanisms for alcohols and talk more about the mechanism and writing the products. And my hope is to put a few homework problems online now that we can also talk about on Wednesday in class.